Hi, my name is Jonathan, and today I'll be reading article Viewpoint: Software Engineering and Machine Learning Systems by Charles Isbell, Michael L. Littman, and Peter Norvig. So starting off, machine learning (ML) is ubiquitous, contributing to society-facing applications that each day impact how we work, play, communicate, live, and solve problems. 2015, after Mark Andreessen proclaimed software is eating the world, others countered machine learning is eating software. While there have been, sorry, been exciting ACM, AM, Turing Award-winning advances in the science of ML, it is important to remember ML is not just an academic subject. It's technology used to build software that is consequential in the real world. So as I reflect on this paragraph, able to see that although it's taught in school, especially at universities such as Georgia Tech, it's also very applicable to the real world and very important to how society is going to advance. Continuing, failures of ML systems are commonplace in the news. IBM's oncology expert advisor project is canceled for poor results after a $60 million investment. The chatbot Tay learns abusive language. An Uber self-driving car runs red light. A Nightscope security robot knocks over a toddler. Facial recognition systems unfairly make 3 times more errors for non-white males. And you can see here there's a lot of bias. I mean, so there's a lot of implications as well with ML. So you got to be careful. So for 50 years, the software engineering community has been learning from its own failures, introducing new tools, techniques, and processes to make better software. To build robust, reliable, safe, fair systems with ML, we need to establish these. We need all these established software engineering techniques and some new ML specific ones. In turn, software engineers should realize how ML can change the way software is developed. Our goal in this viewpoint is to pull together some of the threads that relate to this topic to spur more conversation about putting these ideas into practice. Ignoring these insights will lead to unprecedented levels of technical debt. In brief, we believe that ideas from software engineering, such as explicit requirements, testing, and continuous integration, need to be embraced by teams that are making systems built on top of data. Software engineering basics. Some organizations, machine learning researchers develop ML algorithms using R or Python notebooks without basic software engineering tools like type checking, reusable modules, version control, unit tests, issue tracking, system and process documentation, code reviews, postmortems, automated hermetic builds, and continuous monitoring. This lack of discipline is an avoidable source of failures, or organizations should insist on standard software engineering practices from their ML teams. Machine learning researchers should be encouraged to use the same tools and pipelines that will be used in production, heeding the emerging machine learning operations techniques, ML ops techniques. As the NASA saying goes, test what you fly, fly what you test. Including software engineering education as part of the data science curriculum will help newly minted students appreciate how important these processes are to help them meet their responsibilities. And you see here on the left side, distinguished speakers program. Great speaker can make the difference between a good event and a wow event. Um, okay, next paragraph. Taking data seriously. Every software program deals with issues of verifying data, keeping it secure and private, scaling up to big data when needed. But in ML, the stakes are raised because algorithms learn from data. So data error can lead not just to a problem for one customer, but to decreased performance for every customer. And as I reflect on this paragraph, I can see that the type of data that you're sourcing from is very important. And also what data that you want to use affects is it's like a domino effect. If you're feeding in data that's not sufficient, it's not up to par, then as a result, what you're going to get out of it, the results are just not going to be as effective because your data that you're training your algorithm off of is not effective. Continuing, organizations should employ a data pipeline that tracks the provenance of all data, allows it to be annotated, managed, and abstracted, protects the privacy of personal identifiable or proprietary data, promising technologies including differential privacy, federated learning, and homomorphic encryption are key tools for privacy, but are in various stages of maturity. ML teams must have separate training, validation, and test data sets, which should not accidentally become intertwined as the design space is explored. Teams can fool themselves by running experiments until the results look good and then stopping. At that point, they cannot be sure if the last good results are truly representative of future performance or if the results will regress back to the mean. Teams must protect themselves by adhering to experimental design and stopping rules. This makes sense. Because you want to, there has to be governance. You need to make sure that you're following the right rules, documenting properly in order to get the best results that you can possibly. Many ML algorithms include randomness, so different training runs may produce different results. More thorough testing is needed as a consequence. Throughout the development process, developers must acknowledge that the fingerprints of the human engineers are all over the final result, for better and for worse. When example data comes from users, ML systems are vulnerable to mistakes and intentional attacks by these users. The site labelerrors.com catalogs labeling errors in popular crowdsourced image databases, such as labeling a dingo as a coyote, which corrupts systems that train on this data. It's like the domino effect I'm seeing. Worse, adversaries who can contribute as little as 1% of the training data can poison the data, allowing them to exploit an ML system such as an email spam filter. To guard against these attacks, we must verify data as well as software and promote adversarial thinking throughout the educational pipeline so system designers know how to defend against malevolent actors. Optimizing the right thing. In traditional software engineering, the requirements say what should be achieved, and programmers design and develop an implementation that meets the requirements, verifying their choice of how satisfies what must be done. With ML, computation becomes a partner in this translation process. Programmers state what they want achieved by supplying training examples of appropriate and appropriate behavior and defining objective function that measures how far off the implementation is from requirements. A learning algorithm then takes the training examples and objective function and compiles them into a program that ideally produces success on future examples. If we get the data and requirements right, the software writes itself. So similar to the software engineering process, documentation, requirements engineering, finding the use cases. It's just different practice because I'm training algorithms that I'm seeing. Fortunately, the reality of ML is it is difficult to precisely and unequivocally say what you want. ML algorithms will exploit loopholes in the requirements. A Roomba that was instructed not to bump into furniture learned to drive backward because there were no bumper sensors on the rear. Video game playing programs were instructed to achieve the highest score and did so not by playing the game, but by writing their names in the list of high scorers. Expressing requirements as an objective function can service their latent contradictions. For example, the law requires equitable treatment of protected classes in employment, housing, and other decision-making scenarios. When writing requirements for a system to predict whether a defendant will commit a crime in the future, we need to translate this equitable treatment law into an objective function. One requirement is that predictions are equally accurate for both black and white defendants. Another requirement is that the harm done by bad prediction affects black people and white defendants equally. Unfortunately, it is not possible to achieve both these requirements simultaneously. ML developers in consultation with all stakeholders must decide how to make trade-offs and objectives. Interesting. Um, wow, okay. There's many implications here. But I think as technology gets better, um, the data sourced becomes more is better. There might be, I think ML has a good chance um becoming better. Yeah. Building trust. A successful software system must not only get the right answers, but also convince the developers and users to trust the answers. This has been very important. Trust. You gotta get people to understand that these algorithms are here to help, not harm. So, as ML software is increasingly being tasked with highly sensitive decision making in areas such as hiring, medical treatment, lending, and criminal sentencing, we have to ensure such fair systems are fair, transparent, accountable, auditable, explainable, and interpretable. We must determine what sorts of explanations will justify treatment of an individual, what kind of tests will certify robust systems, performance across likely use cases, what type of auditing or reporting will demonstrate fairness across diverse protected classes, and what remediation processes are available when there are errors. Doing so is difficult because ML systems are often used for the most complex and ill-defined tasks. If the tasks were easy, we would not need an ML solution. Okay. For example, despite enthusiasm for ML classifiers and medical imaging, and despite many systems achieving 95% plus accuracy, there are still few deployed systems because ML engineers have not yet convinced doctors the systems are robust across different X-ray machines, different hospital settings, and so forth. Without better assurance, there is insufficient reason to believe such high accuracy will persist in the wild, resulting in poor outcomes. This makes sense. I can see ML in the future just enhancing the workflows for people. I don't think it's going to completely replace it because nothing can replace human judgment, but it will help enhance human judgment. People are able to have more clarity when they make a judgment. Traditionally, programmers try to write code that is generally enough to work, even in cases that were not tested. In ML systems, it's hard to predict when a training example will generalize to other similar outputs and when the example will be memorized by the system with no generalization. We need better tools for understanding how ML systems generalize. In traditional software, major updates are infrequent, leaving sufficient time to thoroughly test them. Small patches are localized and thus only require testing the parts that are changed. But in ML systems such as internet search and product recommendations, new data is arriving continuously and is processed automatically, often resulting in unbounded non-local changes to ML models. ML developers need to be prudent about how often they retrain their models. We need better tools for understanding how ML systems generalize. Um, ML developers need to be prudent about how often they retrain their models on new data. Too frequently and would be difficult for quality assurance team to do thorough testing. Too rarely and models become stale and inaccurate. Interesting. Um, I'm curious to see like what's the perfect timing. It's probably dependent on the solution, but it'd be interesting to see. We need better tools for tracking model evolution. In addition, for tracking new data, we need a process for discarding old data as when a major event like a social media platform or pandemic significantly alters the data models rely on. Avoiding downstream trouble due to such data cascades takes vigilance, as well as inputs from domain experts and software and from software fields such as human-computer interaction. Verification of traditional software relies on abstractions that let us divide the system into components that are composable, modular, interpretable, and often reusable. Current methods for building ML systems do not typically lead to models with these properties. Rather, each ML system is built from scratch, and each resulting model is largely a black box requiring significant work to understand and verify. One promising approach is a class of multitask unified models that share internal structure across related task datasets and languages. More effort can go into verifying a single large model, which can then be specialized for new tasks. Diverse viewpoints. It's easy to create, say, a calculator program because all users agree that the answer to 12 times 34 should be 408. But for many ML problems, the desired answers are personalized for each user. Interesting. That means we need to do balanced data collection, particularly for underrepresented groups, to ensure that each group gets the answer they need. We cannot let the data of the majority undermine proper answers for the minority classes. That's very true. Can't The algorithm can't have bias. It's important, like the type of data, the sourcing, um, just where the data comes from, and what kind of data that you want to look at, and what kind of data that should be trained off is very important. Is what I'm learning from this article. To probably serve a diverse population of users and use cases, ML development teams should be diverse themselves and should be trained to consider diverse needs and not to be satisfied with existing data sets that are unbalanced in their coverage. This makes sense. Different use cases, like the requirements engineering part. There's a lot of use cases that because of the diverse backgrounds, everybody that people that from one background never thought of, another one can bring up. And it's also important that data that the ML model is constantly, not constantly, but like constantly being updated in their training because it's important for the model not to go stale, but also just finding that balance to make sure that the QA teams aren't working overtime to process this data and make any errors. Society needs us. There can be many sources of bugs in ML programs. Traditional bugs in the implementation of the algorithm, invalid, incomplete, or unrepresentative data, incompleteness in the specification of objectives, poor choices of hyper parameters, and more. Now that ML software is rapidly expanding in its prevalence, consequence, and influence on our lives, it is clear we need careful professional methodologies designed to encourage the positive while moderating the negative impacts of this technology on society. We must build tools to support these methodologies, train people to use them, and develop certification systems that reassure users and minimize failures. Making ML dependable will require new research and new practice. It will require new machining Machine learning researchers thinking like software engineers and software engineering researchers thinking like machine learning practitioners. The consequences are too dire to do anything else. Overall, I love this article. Learning a lot. I have different perspective on ML. Needing to make sure that these programs follow different use cases, that they're diverse. Um, Diverse groups are working on them, and just like the quality of the data is just super important to how well an ML model is. It's different than a software system for sure because um, sometimes, for example, it mentioned earlier, the model can generalize. So yeah, I love this article.